As our second session, in this project, we will investigate the Poiseuille flow in a pipe using the concept of axisymmetric simulation. Now, in this type of simulation, our geometry is in 2 dimensions, but the software will consider it as a 3D object, with the advantage of lowering our computational cost. In this project, we also enable the energy equation and calculate the Nusselt number value on the wall of the pipe. Now, as our first step, just like the previous project, we click on Fluid Flow block and drag it into the blank space, and double-click on the geometry part. If you can remember correctly, in the previous project, we created our geometry using the sketching method. Now, in this project, we will create our geometry using points. To create a point, we click on Create button and then select Point. After selecting the command point on the lower left side of the software window in front of the definition, we change it to manual input. After that, under the point group section, we enter the coordinates of our first point, which would be on the starting point of our coordinates. After entering the values of x, y, and z, as you can see in this window, we click on Generate, and the software will create this point for us. Now we need our second point. To create that point, just like the previous slide, again we click on Create and then select Point. Now again, in order to be able to enter the coordinates of our second point, we again change the definition section to manual input. Now this time, in front of the y coordinate section, we enter the value of 0.02 meter, since we want our pipe to have a radius of 2 centimeters. And since we want the length of our pipe to be equal to 2 meter, we enter the value of 2 in front of the x coordinate section. And finally, for the last point, we again click on Create and then select Point. Again, in front of the definition, we change it into manual input. And in front of the x coordinate, we enter the value of 2 meters. And in front of the y coordinate section, we enter the value of 0.02 and click on Generate button so that the software will create our last point. Now that we have created our 4 main points, which are the main vertices of our geometry, it's time to turn these points to lines. To do that, we click on Concept and then select Line from Points. Also, in order to have a better view of our 4 points, we click on Zoom to Fit button. After selecting the Line from Points command, we click on one of the points on either side, and while holding down the Control key, we click on the other point. After selecting the pairs of points on 2 sides, we click on Apply and then click on Generate, and the software will create a line for us between each of these points. Now, in order to create a line between the upper points and lower points, just like the previous slide, we follow the same step and then click on Concept and click on Lines from Points. Now, after selecting the pairs of points on the top and bottom side, we click on Apply and then click on Generate, just like the previous slides. Now that we have the outline of our geometry, it's time to turn these lines and outlines into the surface. To do that, we click on Concept and then select Surfaces from Edges. After that, while holding down the Control key, we select our 4 edges of our geometry. After selecting all the edges, we click on Apply button and then click on Generate. There's one point worth mentioning, which is that when we've created our geometry and that we want to take it to the meshing software in order to create mesh for it, we should pay attention not to take any redundant bodies there, for it may cause us small problems in the simulation software and process. For example, in this project, if you expand the part section, you can see that two parts exist here: line body and surface body. Now the line body here is the redundant body, and that we should somehow delete it. To remove this body from the list of bodies that we want to take into the meshing software, we right click on it and then select suppress body. And now the final task is to change the type of our surface body from solid to fluid. That was the final step, and now we gotta save our project. After saving the geometry of your project in the Design Modeler software, we close it. After closing the Design Modeler software, it's time to open the meshing software. To do that, we double click on the mesh button. Now, just like the previous project, in order to determine the number of mesh cells over an edge, we right-click on Mesh button and select Sizing. After selecting the Sizing button, while holding down the Control key, we select the edges that are placed on the left and right side of our geometry. After selecting these two edges in front of the geometry, we click on the Apply button, and then underneath it, in front of the Type section, we select Number of Divisions. In front of the number of divisions section, we enter the value of 20 so that the software will create 20 mesh cells over these edges. After entering the number of mesh cells over these two edges, in front of the behavior, we select the hard behavior, and in front of the bias type, we select the first option. Now, if you can remember, we select the bias option when we want to create a boundary layer mesh manually. And since in this project we are only modeling the upper half of our pipe, we have to create a boundary layer mesh where has a smaller cells near the wall boundary, which would be the top boundary. And in front of the bias factor, we enter the value of 3 so that the biggest mesh cell over these edges has a width 3 times bigger than the smallest cell. Now, if you zoom a little bit over one of these edges, you can see that the direction of mesh cells are not correct here. Since we wanted to create a smaller mesh cells near the wall boundary, which would be the top boundary. To solve this problem, we click on Reverse Bias and then select this edge and then click on Apply again. And you will see that the software will automatically change the direction of mesh cells here. Now, in order to make sure that the other edge has the correct form of mesh direction, we click on Pan button and then drag the geometry to the other side. And now over this edge, you can see that the mesh direction is correct and that we don't need to change anything. Now, in order to determine the number of mesh cells over the top and bottom edges, we right-click on Mesh and then select Sizing again. If you have problems selecting an edge, all you have to do is to select and click on Edge button. After that, the software will understand that you only want to select an edge and will not show or select a surface, for example, for you. After selecting the two edges simultaneously, we click on Apply, and then in front of the type, we change the element size to number of division, just like the previous two edges. After that, in front of the number of division section, we enter the value of 1000 so that the software will create 1000 mesh cells over these two edges. After this, in front of the behavior, we change this from soft to hard. Now, in order to better capture the starting point of our boundary layer, we need to use the bias option in order to make the mesh cells near the inlet boundary smaller. To do that, we click on bias type and then select the first shape. Now, in front of the bias factor, we again enter the value of 3, just like two previous edges. Again, if you zoom a little bit over these two edges, you can see that the same problem exists here again. To do that, we click on reverse bias again and then select the edge where we want to change the mesh direction. And for the final step, just like the previous session, we right click on mesh and then select insert and then go over and select face meshing so that the software will understand that we want quadrilateral mesh on the surface of our geometry. After selecting the face meshing command, we select and click on the face of our geometry, and then in front of the geometry we click on apply button. Now that we have created all the options and settings that we wanted to create in our geometry, we click on generate button so that the software will create the mesh for us. Now if you zoom a little bit over one of the sides of our geometry, you can easily see the boundary layer mesh that we have created in this geometry. So as was explained in the previous project, if you click on the statistics, you can see the number of mesh cells that exist on your geometry. As you all probably know, it's time to create name for our boundaries. To do that, we click on Edge button and select the left edge. After selecting this edge, we right click on it and then select Create Name Selection and select this edge to be the inlet boundary. After that, we select the upper wall and click on Create Name Selection and give it the name of wall. Now, as was previously mentioned about the bottom wall of this geometry, it has the role of a rotation axis for this geometry. So all you have to do is to click on it and then right click and then select Create Name Selection and enter the name of axis so that the Fluent software will understand that this is the rotation axis of our geometry. And for the final edge, which would be the right edge, we click on it and then select Create Name Selection and name it as Outlet. And for the last step of giving names to our geometry, we gotta select the Face button and then click on Face of our geometry and give it the name of Flow, since this is the passage of our fluid flow. Now that we have created mesh cells for this geometry completely, we close the ANSYS meshing software. Now sometimes when you close the ANSYS meshing software, you will confront with this view, where there is a lightning symbol in front of the mesh. To solve this problem, you just have to right click on it and then select Update. Now in order to open the Fluent software and adjust the settings for our project, we double click on Setup. In the appeared window under the options, you can see that again the double precision option is enabled, and in front of the solver processes you can enter the number of CPU cores which you want to use for solving and calculating the parameters related to your project. By clicking on check button, you will see that under the console tab, the Fluent software will start to check your mesh for any errors. Also, by clicking on report quality, again in the console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. Now under the 2D space, we select the Axisymmetric option, since our geometry has a rotation axis and that we want to calculate the related parameters to fluid flow in cylindrical coordinates. In this project, under the Model section, we enable the energy equation since we have heat transfer inside our domain. And if you double click on the Viscous button in the appeared window, you can see that we select the laminar model, since the fluid flow entering our computational domain does not have a high velocity and does not, therefore, have high Reynolds number. Now we want the water to be the material that flows inside our pipe. Therefore, we need to add this material. To do that, we expand the materials and then go over Fluid and right click on it and then select New. Now in the appeared window, by just going and clicking over the Fluent database, we easily can add the water material from the list of available materials in the Fluent software. Now, in this list, look for the water liquid material. After selecting that material, by clicking on Copy, your material will be copied to the software. Now, in the main window for the material section, we change the values of density and viscosity to 1000 and 0.001 so that we can calculate the Reynolds number easier. Now that we have added the water liquid material, it's time to introduce this material into our computational domain. To do that, we expand the fluid under the cell zone condition and double click on the flow button, and then in the appeared window in front of the material name section, we need to change it from air to water liquid. In the boundary conditions section, if you click on the inlet boundary, you can see that the type of this boundary is defined to be velocity. By clicking on Edit button, a new window will appear in which you can change the settings for this boundary. Now, using the correlation, which shows the relation among the length needed for the flow to reach fully developed state and the diameter of the pipe and Reynolds number, we can calculate the Reynolds number if we want our fluid flow to reach fully developed state at distance of 1 meter from the inlet boundary, which will be equal to 500. Now, if we put this value of Reynolds number in the Reynolds number equation itself, we can calculate the velocity of the fluid flow entering our pipe. Now, if you click on the thermal tab, you can change the temperature of our fluid flow, which we will set it to 298.15 Kelvin or 15 degrees centigrade. Now, if you click on the interior flow and then click on edit button, in the appeared window you will see that no settings will appear and that you don't need to change anything. Now, if you click on outlet boundary and then click on edit, in the appeared window the most important point you should pay attention to is the gauge pressure, which is equal to 0. Now, the difference between gauge pressure and total pressure and atmospheric pressure were explained in previous session completely. Now, if you click on the thermal tab, you will see that backflow total temperature is shown here. Now, backflow total temperature refers to the temperature of the environment outside our computational domain. Normally, changing the value of backflow doesn't have any effect on our simulation process. But, for example, for problems where the pressure inside your domain is less than the outlet boundary, you will have backflow to your domain, and therefore determining the value of backflow temperature will be of great importance. Now, for the wall boundaries, if you click on edit button, under the momentum tab, we set the stationary wall motion along with no slip shear conditions. And if you click on the thermal tab, you can see that we have selected the heat flux thermal condition, and we have set the value of heat flux applied on this wall boundary equal to 5000 watt per meter squared. Now, this heat flux is directly applied to the outer layer of our fluid flow. Now, for those of you who might ask, what if we have a pipe and we are applying this heat flux to the outer layer of our pipe? Then, in order to simulate the solid part, you just have to define the wall thickness. And then, under the material name, define the material of your pipe. After double-clicking on the method, you will see that a new window will appear showing you the pressure-velocity coupling. Also, you can see that the spatial discretization methods are shown in this window. Also, you can change this discretization into other formats, like you can change them into first order event and the other options available for each variable under their combo list. And for the simple pressure velocity coupling, the simple algorithm is kind of an iterative solver which uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. After double-clicking on the Controls button, in the middle section of the software window, you can see that new part will appear. In the Appear part, you can see under relaxation factors for different parameters. Now, these values are set here by the software automatically. You can change these values, which are between 0 and 1, by yourself for different projects you do. But it is highly recommended that you do not do that, since it may result in divergence. Now, in order to define a report for monitoring the changes in average temperature, all we have to do is to right-click on Report Definitions and then go over New and then Surface Report and then select Facet Average. Under the field variable, we select the temperature, and under the surfaces, we select the outlet boundary so that we can monitor the changes of temperature at the outlet boundary. Now, in order to see this report when you're solving your problem in the graphic view, you have to enable the report plot. And if you want to save this plot, you have to enable the report file too. After double-clicking on the residuals button, a new window will appear. In the appear window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. In this project, we disabled the check convergence for all of these parameters from continuity to y velocity and x velocity and energy, since we want the software to finish all the iterations that we interpret, and that we do not want the software to stop even when the parameters have reached their absolute criteria of convergence. Now, if you double-click on the initialization button in the appear card, you can select between hybrid and standard initialization. Now, the difference between these two was explained in previous session. In this project, we will select the standard initialization method. Now, in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the compute from drop-down list and clicking on one boundary. For example, by clicking on compute from all zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software. Now in this project, under the compute from list, we select the inlet boundary. Also under the initial values, you can see that the parameters of axial and radial velocity are shown. Now if you can remember correctly, in previous slide we talked about the axisymmetric simulation method, in which the software will use cylindrical coordinates in order to solve the fluid equations. Now after we click on initialize button, we double click on run calculations, and under the number of iterations section, we enter the value of 600 and we click on calculate button so that the software will start the simulation process. Now after the simulation process ended, in the graphics view, if you click on report plot number 0, you can see that the changes of average temperature at the outlet boundary has reached the constant value, which is a sign that our simulation process has reached convergence. Now in order to create and extract contours, just like as it was explained in previous session, we expand the graphics and then go over contours and right click on it and then select new. In the appear window under the contours of section, we select our desired variable, which in this slide we are going to select velocity. After that, under the surfaces section, there is no need to select any surface, and then click on save or display button. Now in the appeared contour, you can see that only half of the pipe is shown, as it was in its geometry. In order to see the other half, you just have to click on View tab, and then go over Views and click on it. In the appeared window, under the mirror plane section, we click on Axis and then click on Apply. You can extract the temperature contour just like the previous slide and change the variable from velocity to temperature under the contours of section and then click on Save or Display button. Also, as it was explained in previous session, in order to extract the velocity vectors, you just have to right click on vectors button and then select new. Now in the velocity vectors contour, you can easily see that the shape of vectors are in a way that shows that the fluid flow has reached the fully developed state. Now in order to extract the value of maximum velocity of the fluid flow at the inlet boundary, we expand the report section and then go over surface integrals and double click on it. In the appeared window, under the report type, we change it to facet maximum, and under the field variable, we change it to velocity. After that, under the surfaces, we select the outlet boundary and click on compute button. Now, as we know from the theoretical solution, the value of the maximum fluid flow velocity after it has reached a fully developed state is 2 times bigger than the average velocity. Now, if you do the math, you can see that the maximum value for the fluid flow velocity is equal to 0.025, and if you compare it with the value that the software has given us, you can see that a very little difference exists between these two. Now, in order to calculate and extract the value of Nusselt number over the walls of this pipe, we have to correct the reference length for this project, which is equal to the diameter of the pipe. To do that, we double click on reference values, and in the appeared part in front of the length, we enter the value of 0.04, which is equal to the diameter of the pipe. After correcting the value of reference length, we again click on Surface Integrals button, and in the appeared window under the report type, we change it into facet average, and under the field variable, we change it into wall fluxes, and underneath it, we select the Nusselt number. After that, under the surfaces section, we click on wall boundary, and then click on compute button. Now the value you see here is the average value of Nusselt number. You also can see the values of local Nusselt number along the wall boundary. To extract the diagram of changes in local Nusselt number along the wall boundary, we expand the plot and then double click on XY plots. In the appeared window under the y-axis function, we select wall fluxes, and underneath it we select Nusselt number. After that, under the surfaces section, we select the wall boundary. In this diagram, you can see the values of local Nusselt number having a very high value at the inlet boundary and almost nearing a constant value at the outlet boundary. To benefit from Mr. CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.